This video is for Chemistry in the Earth System, Unit 1.2, Thermochemistry. Today's essential question is, what is the relationship between a system and its surroundings? Hello, baby birds! In today's lesson on thermochemistry, where we will explore how energy moves, transforms, and interacts with matter during physical and chemical changes. To ground this lesson into real life, let's imagine two events, something that we've already mentioned before. First, let's think of the Hanabi Taikai, the traditional summer fireworks festivals in Japan. A quiet evening sky erupts with colorful explosions. What you're seeing in that moment is chemical energy rapidly converting into heat, sound, and light. It's an exothermic reaction that vividly demonstrates energy release into the surroundings. Now, think of making ice cream using salt and ice, which is a method commonly used in the United States and Europe. The salt lowers the freezing point of the ice, and in doing so, the system draws in energy from the cream, cooling it and eventually freezing it. This is an endothermic process where energy is absorbed from the surroundings into the system. Both of these are perfect examples of how energy exchanges operate in the real world. So in this video, let's explore how these kinds of exchanges obey the laws of thermodynamics and how we model them using systems and surroundings. Let's begin with the most fundamental idea. Energy cannot be created or destroyed. Again, our most fundamental idea is known as the first law of thermodynamics, which is also known as the law of conservation of energy. Either way, in both physical and chemical changes, again, whether you're burning wood, charging a phone, or mixing vinegar with baking soda, the total amount of energy remains constant. It might appear as if energy is being produced or lost, but in truth, it's only being transformed from one form to another. Let's revisit our firework example. Chemical energy stored in the compounds exists inside the firework shell, like potassium nitrate or magnesium or whatever. But that chemical energy that's being stored is transformed into several new forms of energy, like thermal energy that heats the surrounding air, radiant energy in the form of colorful light, and sound energy to form that explosive boom that you hear. But no energy was, quote, created, end quote, because the total amount of energy in the system and surroundings remained constant. A common misconception students often have is saying energy is produced during combustion. But scientifically, we know that energy is simply changing form, not being born or destroyed. Now let's break down chemical reactions into two broad categories based on their energy flow, using terms that you've already heard. First, exothermic reactions. These reactions release energy into the surroundings. The chemical bonds in the reactants contain more energy than those in the products. So that excess energy is released, usually as heat or light. Common examples include fireworks, like the Hanabi Taikai, in which chemical energy becomes light and heat. Another example would be rusting iron, which is actually a very slow release of energy. Light sticks, in which chemical energy becomes visible light through luminescence, or the combustion of fossil fuels. The other type of reaction that we have is the endothermic reaction. Endothermic reactions absorb energy from their surroundings. In this case, the products store more chemical energy than the reactants do, meaning thermal energy is taken in to make the reaction proceed. Some examples of this include photosynthesis, in which sunlight is absorbed in order to form glucose. Also, melting ice, in which the water is absorbing heat in order to change state. And then our other example for this video, traditional ice cream making, in which energy is absorbed from the cream, which goes into the salt ice mixture in order to freeze it. These reactions show how energy can flow into or out of systems depending on what kind of transformation is occurring. To analyze energy exchanges, scientists divide the world into the system, which is the part that we study, like the fireworks shell or the ice pack. The other part that scientists divide the world into is the surroundings, which is everything else, like the air, the observer, or even the environment. This denotation helps us understand where the energy is coming from and where it's going. When we talk about systems, we also define them by how they interact with their surroundings. And we have three types. We have open systems, in which both matter and energy can cross the boundary. An example would be a cooking pot without a lid, in which case heat escapes and ingredients can be added. We also have a closed system, in which only energy can cross that boundary. In this case, mass stays inside. An example of a closed system would be a pot with a lid on the stove. Heat will enter, but the ingredients stay sealed. Number 3, isolated systems. In an isolated system, neither energy nor mass crosses the boundary. These are rare, but a high-quality thermos or other such insulated bottle prevents heat loss. Those come close. In our fireworks example, the fireworks shell before ignition is a closed system, but once it explodes, it becomes open. For the ice cream example, if we seal the churn and insulate it well, it acts like a closed or semi-isolated system, preventing heat from leaking in and maximizing the freezing effect. Now let's look at a familiar real-world process, a car engine. Gasoline stores chemical energy in its molecular bonds. When the engine ignites it, combustion occurs. Remember, combustion is an exothermic reaction, during which chemical energy is released and transformed into thermal energy, which heats the engine and the air. This is why running cars are hot. It also transforms into kinetic energy, which then moves the car. However, some quote-unquote lost energy heats parts of the engine, like the hood. This reminds us that not all transformed energy is useful. So even though kinetic energy moves the car, the rest disperses as waste heat. This shows how energy, once transformed, often becomes less concentrated and less useful, which is a theme we'll return to when we talk about entropy. Now, we'll turn to the second law of thermodynamics, which introduces a powerful concept, entropy. Entropy is a measure of disorder or randomness within a system. According to the second law of thermodynamics, in any natural process, entropy increases. Energy naturally flows from hotter objects to cooler ones, never the reverse, unless some sort of external energy is added. That's a simple caveat. Over time, energy becomes more evenly distributed, meaning warm parts cool down and cool parts warm up. Imagine a sparkler firework burning. At first, all the energy is concentrated in that sparkler, but after a few seconds, it spreads out into the air in the form of heat, light, and sound. That is entropy increasing. Or think of hot coffee sitting on a counter. The heat spreads into the mug, but then to the air, until everything reaches the same temperature. That's because energy seeks stability. But what is temperature exactly? Temperature is a measure of the average kinetic energy of particles in matter. Remember, higher temperature means faster moving particles, and lower temperature means slower moving particles. When two objects of different temperatures touch, energy transfers from the faster particles, meaning the hot object, to the slower ones, meaning the cold object. This continues until both objects reach the same temperature, which we call thermal equilibrium. In traditional ice cream making, salt lowers the freezing point of ice, creating a very cold brine. This brine absorbs energy from the cream, which slows down its particles and causing it to freeze. This transfer of energy occurs until equilibrium is reached, aligning perfectly with both of the thermodynamic laws that we've covered so far. Now let's explain how energy moves between objects. Remember, we've already gone over the three methods of heat transfer. 1. Conduction, which is transfer through direct contact between particles. This happens mainly in solids. A common example, touching a hot stove or touching a metal canister of an ice cream churn as it gets cold. Number 2, convection, which is transfer through fluid motion. Remember, fluids include both liquids and gases. Don't forget the gases. Warmer fluids rise due to their lower density, and cooler ones sink due to their higher density. Some common examples include hot air balloons or warm ocean currents. And then our last method of heat transfer is radiation. This is transfer through electromagnetic waves, and this does not require a medium. An example of radiation includes heat all the way from the sun, or the glow of fireworks that you can feel even from far away. All three methods may be happening simultaneously. For example, in a firework, conduction heats the shell, convection carries the hot gases upward, and radiation spreads light and infrared heat to your skin. Now let's apply this knowledge to two practical examples from daily life. Example 1. An ice pack on an injury. In this case, the system is the ice pack. The surroundings are your skin and the air. In this example, the ice absorbs energy because it's endothermic. That cools your skin and thereby reducing swelling. As the ice melts, it draws heat from your leg or wherever you're injured. The total amount of energy in the universe remains the same, but the energy has moved from the surroundings to the system. Example 2, hot coffee in a cup. In this example, the system is the coffee and the cup. The surroundings are the air, the table, and your hand. In this example, the hot coffee transfers heat to the cup via conduction and to the air via convection as well as radiation. In this example, eventually, the coffee cools and everything reaches the same temperature. This demonstrates both conservation of energy and entropy increase. So let's wrap up the key concepts for this lesson. First off, the first law of thermodynamics, which states that energy cannot be created or destroyed, only transferred or transformed. Then we have the second law of thermodynamics, which states that entropy always increases, meaning energy naturally spreads out. Next, we have the idea of systems versus surroundings. This helps us define where energy is and coming from. Then we have the idea of exothermic versus endothermic reactions. These tell us if energy is being released or absorbed. And lastly, heat transfer happens through conduction, convection, and radiation. Together, These ideas help us explain energy flow in chemical reactions, in your daily life, and in cultural traditions like fireworks or ice cream making. So let's bring this back to where we started. Hanabi Taikai, the Japanese firework festival, is a beautiful example of an exothermic reaction. It demonstrates energy stored in chemicals transforming explosively into light, heat, and sound, as well as traditional ice cream making using salt and ice. This is a practical example of an endothermic process. It shows how energy can be drawn in from the surroundings to create coldness and change the state of matter. These events are rooted in culture but governed by universal scientific laws, which we call thermodynamics. These thermodynamics unite the scientific and the everyday. So, the next time you see something heating up, cool down, or change form, ask yourself, what is the surrounding? What is the system? And where is that energy going? At this point, you should be able to generate a full and appropriate response to today's essential question. What is the relationship between a system and its surroundings?